So the next operation that we want to talk about with vectors is vector addition. So here's some motivation. To understand the scaling operation for vectors, we came up with a way to decompose vectors into a unit vector, providing the direction, and a scalar, providing the length of our vector. Combining this with what we know from our two-dimensional walking game, we can construct an intuitive way to describe our vectors using the orthogonal directions with which we are more familiar. Recall that we declared a two-dimensional vector v equal to xy to be an arrow that points from our starting location in R2 to an ending location in R2 using the set of instructions move x steps horizontally, move y steps vertically. So we can use two special unit vectors to encode these movements with scaling. So Vx represents the motion in the x direction, and Vy represents the motion in the y direction. If we started from the origin, then we can envision our movement as something like the following picture. In R2, we could reasonably call the vectors Vx and Vy the projections of V along x and along y. Now, if we add in the most obvious fashion, then we could also represent the vector v as the sum of these projections. So here we've simply added the components. So we add the x component of vx to the x component of vy. We've added the y component of vx to the y component of vy. Our familiarity with R2 tells us that just like addition of real numbers, this addition should in fact commute, which is to say the order in which we add vx and vy should not matter. Geometrically, that is to say, our intuition tells us that if we were to follow these instructions in the opposite order, we should end up with a parallelogram leading to the same point in two equivalent ways. We would like to ask the question, given two vectors, v, which is x1, y1, and w, which is x2, y2, can we, given the component-wise sum of these two vectors, make sense of v plus w geometrically? So once again, we appeal to our two-dimensional walking game. On the one hand, starting from the origin, we can move as described by the vector v, then move as described by the vector w. So first, we move x1 steps horizontally, then y1 steps vertically. The arrow v points from the origin to our new position at x1, y1. Then the vector w instructs us to move x2 steps horizontally, then y2 steps vertically. So we get an arrow w that points from our previous position, x1, y1, to our new position, x1 plus x2, y1 plus y2. And we can think of the vector v plus w as the arrow that points from the origin directly to our final position at the tip of w. Now, on the other hand, we could have thought about starting from the origin, moving according to the instructions encoded by w, then moving according to the instructions encoded by v. So that would have us first move x2 steps horizontally, then y2 steps vertically. This would give us an arrow, w, that points from the origin to our current position at x2, y2. Next, we move x1 steps horizontally, then y1 steps vertically. This gives us an arrow v that points from our previous position at x2, y2 to our new position at x2 plus x1, y2 plus y1. Now we note that because addition commutes, these two ending points are exactly the same point. So as a result, we can see that adding vectors is a commutative operation in the sense that v plus w is equal to w plus v. We note that it is natural to extend this definition to vector subtraction. Since the vector minus w is simply the vector w oriented in the opposite direction, we can translate subtraction to addition as v minus w equals v plus minus w, which is the same thing as minus w plus v. So using the techniques we've developed for generalizing to higher dimensions, we're now ready to define vector addition in general. So given two vectors, v, whose components are v1 through vm, and w, whose components are w1 through wm, of the same dimension, we define their sum to be the vector whose components are the component-wise sum of the components of v and w. So just as for R2, we visualize the vector v plus w, or w plus v, as the arrow through the parallelogram in Rm with two sides v and two sides w. For the purposes of later computations, we record here the following property, which is the distributivity of scalar multiplication. So we observe that we can easily see the geometric content of our equality states that scaling the sum of v and w by the same number a is equivalent to scaling v and w by a, then adding them together. While we could provide a geometric proof of this fact, it's much easier to rely on algebra. The core property that we use is the distributivity for real numbers. Since our vector addition is just component-wise addition of real numbers, and our scaling is component-wise multiplication, there really isn't a whole lot to do here. We simply move everything around and then separate. This sort of manipulation will turn out to be very common and very important.